The talk is Past, Present, Future of Breath Testing for Bacterial Overgrowth. So Charlotte's been working at the Functional Gut Group as a gastrointestinal physiologist since graduating from the University of Warwick with a degree in biomedical sciences in 2017. She's been heavily involved with hydrogen and methane breath tests used in diagnosis of small intestinal bacterial overgrowth and carbohydrate malabsorption. As part of the team, she's implemented FGC's first gas chromatography system for analysis of these breath tests for both private and NHS patients. In order to help improve breath testing protocols, she studied breath test data and published performance and interpretation of hydrogen and methane breath testing, impact of North American consensus guidelines, as well as a review of the effectiveness of home testing kits for SIBO, which she presented recently at the British Society of Gastroenterology conference. Sarah is a clinical gastrointestinal physiologist at the FGC Group. She's been a member of the group for 4 years, where she runs regular patient clinics. Sarah's actively involved in many research projects, including the development of next generation breath tests with research into hydrogen sulfide, and is also working towards a PhD in medical sciences with Anglia Ruskin University, investigating the impact of iron supplements on gastrointestinal tract with hydrogen methane breath testing and using Alstom's Biopsy breath testing technology. So over to you both, and thanks again for the time.
Hi, my name is Charlotte. I'm a gastrointestinal physiologist with a functional gut clinic. Myself and my colleague Sarah Bloor will be talking to you about breath testing applications in gastrointestinal physiology across 2 parts. So firstly, I'll be talking about the past and present, where we're currently at with breath testing, and then Sarah will go on to talk about advancements in technology and where breath testing can go in the future. So just a disclosure, firstly, I am an employee of the Functional Gut Group, which provides hydrogen and methane breath testing services to NHS and private patients. So in this talk, I'll be talking about how hydrogen and methane breath testing works, how levels of these gases in breath relate to what's going on within our guts, what measuring these gases can tell us about different conditions, so how we can use these tests to diagnose SIBO, intestinal methanogen overgrowth, and also carbohydrate malabsorption. And I'll also talk a little bit about standardization for these tests and how this is important for ongoing research to improve the quality of the test going forward. So the idea behind hydrogen and methane breath testing is that any gases produced in the intestines can be absorbed across the intestinal epithelium, transported in the blood to the lungs, and then be exhaled within breath. So by collecting samples of the breath and analysing its constituents, it can give us an indication of the processes that are occurring within the intestines. This is how we collect and analyse the breath samples. So a patient will collect their sample by blowing through a straw into a tube. The breath within the tube is then extracted and the sample is analysed through gas chromatography, which measures for the presence of hydrogen, methane, and also carbon dioxide, which we use as a measure of sample validity to ensure that the breath sample is good quality. By analysing the breath samples, it can give us an indicator of functional disorders such as small intestinal bacterial overgrowth, intestinal methanogen overgrowth, or carbohydrate malabsorption associated with things like lactose or fructose intolerance. These are all functional conditions in that the normal gastrointestinal processes are affected to cause symptoms, rather than the structure or the anatomy of the GI system itself. These conditions all present in a similar way, with patients reporting IBS-type symptoms. So hydrogen and methane breath testing is useful to distinguish between these so that the treatment can be better targeted. I'll be talking about each of these conditions in turn and how hydrogen and methane breath testing can identify these. Before I go on to explain more about these conditions, I'm just going to explain a little bit more about the process of digestion. This helps us to explain a little bit more about what we're looking for with these tests and what goes wrong with these different functional conditions to cause symptoms. So what we have here is a diagram of the normal gut. So we've got a section of the small intestine and a section of the colon as well. And all those colourful little dots within the bowel are your foods. So foods such as lipids, proteins, carbohydrates, all the components of a normal diet. What you have within the small intestine is enzymes that are produced by our body naturally break down these foods to help them to be absorbed, so they're absorbed within the small intestine. Food that isn't absorbed, such as more fibrous foods, more complex carbohydrates, they continue into the colon as they can't be absorbed directly, but in the colon there's a high proportion of microbes which ferment to help break down these foods and metabolize them further so that they can be absorbed. Fermentation of these foods in the colon is normal and it's an important part of digestion, and it's when this fermentation becomes inappropriate that it can cause problems, such as in the conditions that I'll be talking about. Foods such as dietary fibre, complex carbohydrates that reach the colon are broken down through the process of fermentation. It's then the byproducts of fermentation that we measure in breath testing as a proxy measure of fermentation and the activity of gut bacteria. The main gas that's produced as a byproduct of fermentation is hydrogen, and in the presence of certain species, this can be processed further to produce things like hydrogen sulfide, methane, or acetic acid. These gases, these byproducts of fermentation, this is what we measure in breath as an indicator of fermentation. So it can tell us how much fermentation is occurring, where this fermentation is occurring, and what substrates this fermentation occurs in response to. So the first condition we're going to be talking about is small intestinal bacterial overgrowth, or SIBO. So SIBO is defined as a higher than normal level of bacteria within the small intestine, causing fermentation to occur prematurely, meaning these byproducts of fermentation, these gases and short-chain fatty acids, are being produced in the small intestine rather than solely within the colon. Excess fermentation occurs as foods that are normally being absorbed within the small intestine are instead being fermented before this can occur. This results in symptoms that are often associated with IBS, so things like abdominal pain, bloating, a change to bowel habit, but can cause more widespread issues affecting the skin, things like rosacea or eczema, things like depression as well. It can also result in malnutrition as your food is being fermented before it can be fully absorbed, which means you're not getting those full nutrients, and you can actually get things like vitamin deficiencies as a result of SIBO as well. So what we have here is a pictorial representation of SIBO. So this diagram here on the top represents a normal bowel, and then the bowel on the bottom represents one with SIBO. So the darkest green colour that you can see represents high levels of bacteria, and you can see in the top image in the normal bowel, this darkest green region is confined to the colon, which is on the right of the image. This means that that major region of fermentation is confined to the colon. In SIBO, the bottom image, the dark green representing the high concentration of bacteria is also within the small bowel, so it's come into the ileum and into the jejunum as well as in the colon, which is increasing this major region of fermentation. So this means that simple carbohydrates, things that like rice, that in the normal bowel would be absorbed completely within the small intestine and not be fermented at all, and now being fermented as the major region of fermentation as this come higher up. And it also means that foods that would normally be fermented within the colon are now also being fermented in the small intestine. So the poorly digestible starch, such as beans, the fermentation of those is also occurring in the small intestine as well. So overall, what we're getting is excessive fermentation within the small bowel. So to look for SIBO with a breath test, we're looking at the byproducts of fermentation, in this case hydrogen, in response to a sugar substrate to identify where the fermentation is occurring. So in preparation for the test, the patient has fasted and has followed a low residue diet for 24 hours, and this reduces the baseline level of fermentation so that we can be confident that any fermentation is occurring is in response to the sugar substrate that we've given them, rather than any ongoing colonic fermentation from something the patient is eating prior to the test. So we'll give the sugar substrate and measure breath gases at different points for around 2 hours. So in a normal person, on the left, you can see in the graph down the bottom, we've got time going across the bottom and then ppm of hydrogen on the y-axis. So as time goes on, there isn't much hydrogen production and the graph is staying fairly flat. And then towards the end of the test, we get a rise in gas production later on as the sugar substrate has entered the colon, is being fermented by the bacteria there to produce the hydrogen. In SIBO, which is the graph on the right, what we can see is an early rise early on in the test. We get this peak, which indicates that the sugar is being fermented earlier on than we'd expect it to, i.e. in the small intestine, and therefore suggested of SIBO. Towards the end of the test, you still get a peak in gases as the sugar enters the colon and is fermented by the large population of bacteria there. So you get that double peak pattern with a small peak indicating small intestinal fermentation and the larger peak as the gases produced from the colon. So in testing for SIBO, a common sugar substrate that would be used would be a lactulose sugar. Lactulose is synthetic sugar, which means it's not absorbed within the small bowel. This means it travels through the whole gut and can give us information about fermentation in the entire of the small intestine and into the colon as well. Because of this, it does come with the risk of false positives. So if a patient has particularly fast transit, lactulose can actually arrive at the colon earlier than you'd expect, causing colonic fermentation to be misattributed to the small bowel, meaning that you'll get a positive diagnosis for SIBO when the fermentation and gas production is actually as a result of that normal colonic fermentation just earlier on than you'd expect it to happen. So the key to distinguishing small bowel fermentation from large bowel fermentation is timing. Whole gut transit time can vary a lot between individuals, so with a SIBO substrate like lactulose, the timing is key to distinguish pathological small bowel fermentation from normal colonic fermentation. This table here shows the variance in orocecal transit time across different populations, and although it can vary, it's typically at least about 60 minutes. So different guidelines have been published recommending different cutoff values for what constitutes small bowel fermentation rather than colonic fermentation. So for example, the North American Consensus, which is a document published in 2017 and aimed to standardize the preparation, performance and interpretation of all hydrogen and methane breath tests, this North American Consensus document assumes an average transit time of 90 minutes and states that a significant rise in hydrogen above 20 ppm within this time is indicative of SIBO, and any gas production after this point can be considered to be normal colonic fermentation. However, prior to this, the guidelines that were followed typically were Ledachowski guidelines published in 2008, which suggest a more conservative 60-minute cutoff point, but that just 10 ppm rise in hydrogen is significant and is sufficient to diagnose SIBO. So it's between the 60 and 90-minute mark and between the 10 and 20 ppm mark where there seems to be a bit of debate of what constitutes SIBO and what constitutes normal colonic fermentation. So this is now looking at some research that I did that was published earlier in this year, which looks at the impact of the North American Consensus, so how changing our practice at FGC in line with these guidelines affected patient results. So in terms of diagnosis of SIBO, we found that the best approach is to actually look at both parameters together. So in patients that tested positive by just one guideline, either by the Ledachowski or by the North American Consensus guidelines, they actually showed no significant difference in associated symptoms compared to those testing negative. Whereas significantly more patients testing positive by both parameters had associated symptoms during the test, about 74.3%. So this suggests that true positives are more likely when they have both the conservative rise of the 10 ppm early on at 60 minutes and also the more significant rise of 20 ppm within 90 minutes. So since doing this research, what we use in our practice now is that a patient tests positive if they're positive by both of these criteria, and in patients that are positive by either one of these standards, we can use the presence of symptoms during the test to help to inform the more borderline result. Next, I'll be talking about breath testing to look for intestinal methanogenic overgrowth, or IMO. So this is a separate condition which is similar to SIBO. It can cause similar kind of symptoms, but it's actually caused by archaea rather than bacteria. And these methanogenic archaea are actually non-saccharolytic, so they don't ferment carbohydrates directly. What they actually do is utilize the metabolic byproducts of bacterial fermentation for their own energy metabolism. So they use bacterial hydrogen, bacterial short-chain fatty acids, those byproducts that we spoke about before, and they use them to produce their own methane. So excessive methane is defined as greater than 10 ppm of methane and is associated with things like bloating, belching, flatulence, the kind of symptoms you'd expect if you're getting excessive gas being produced within your gut, but also symptoms of constipation, and it's also associated with obesity and reduced weight loss after bariatric surgery as well. So unlike SIBO, where the timing of a rise in gas in response to a sugar substrate is key in identifying where the fermentation is occurring, intestinal methanogen overgrowth is diagnosed based on the presence of methane at any point during the test, as methanogens can thrive in the small bowel or the large bowel, and fermentation by methanogens is ongoing rather than substrate dependent. So in my research, the same paper that we looked at previously, we found that in patients testing positive for IMO, significant methane is actually present at baseline, independent of the substrate given, and therefore for people who are just interested in measuring for methane, just looking to see if they've got IMO, a single fasted breath sample is sufficient, as opposed to the full 2-hour SIBO test, which is the common practice to identify methane. The final application of hydrogen and methane breath testing that I'll talk about is in carbohydrate malabsorption. So carbohydrate malabsorption is simply any carbohydrate that isn't fully absorbed in the small intestine, causing the sugar to enter the colon and be fermented there, thus causing similar symptoms to those seen in SIBO or IMO, but in response to specific foods. So lactose is the most common carbohydrate that can be malabsorbed, but other carbohydrates such as fructose or artificial sweeteners can also be malabsorbed in a similar way. Hydrogen methane breath testing for carbohydrate malabsorption measures a rise in breath gases following ingestion of a test substrate, e.g. lactose sugar, to test for lactose intolerance. So a rise in gases indicates that the sugar is not absorbed and the sugar has instead reached the colon where fermentation occurs. So what we see in the graph here, the one on the right, you can see a high production of gas, which indicates that the sugar is being fermented as it's not been fully absorbed within the small intestine. However, presence of bacteria in the small bowel can actually cause false positives for carbohydrate malabsorption, so it's recommended to rule out SIBO first. So looking back on the data that we have on transit time, we can see that oral cecal transit time is typically at least 65 minutes. Therefore, any rise in gas before this point with a carbohydrate malabsorption test could be from gases being produced within the small bowel as a result of bacterial overgrowth there. So with carbohydrate malabsorption, we test by doing breath samples every 40 minutes. If the rise in hydrogen occurs at the first 40-minute point, it could be that it's small intestinal bacteria producing this hydrogen, as at this point you wouldn't have expected that substrate to have reached the colon. So in my research paper that we published earlier this year, we found that in patients testing positive for lactose malabsorption, 34.3% of them saw a significant rise in gas within 60 minutes. And then in patients testing positive for fructose malabsorption, 69.8% tested positive by 60 minutes. So these blue sections on these pie charts are the patients that are potential false positives if SIBO has not already been ruled out. So the North American consensus, that standardization guideline, recommends SIBO testing before malabsorption testing to rule out SIBO first to reduce false positives caused by SIBO. And a carbohydrate malabsorption test alone may actually be not that helpful until you've ruled out SIBO as well. So just a summary of what I've spoken about. So hydrogen and methane breath testing has widespread use in diagnosing gastrointestinal conditions. The presence of hydrogen and methane can indicate inappropriate fermentation in the small bowel, so SIBO, or by methanogens, which is IMO, or an inappropriate response to specific carbohydrates such as lactose or fructose. It's important that we continue our research on these tests so that we can improve their diagnostic utility, and standardization in how we perform, prepare for and interpret these tests is key to helping us get there. I'll pass now on to my colleague Sarah, who will talk about the future of breath testing, so how we can expand these tests to measure some of those other byproducts of fermentation and what more they can tell us about gut health.
Hi, my name's Sarah and I'm a gastrointestinal physiologist at Functional Gut. Today I will be continuing on from Charlotte's presentation about current and past hydrogen and methane breath testing and expanding into the future of breath testing with hydrogen sulfide gas. Just some disclosures. So just a little bit of background first. As Charlotte explained, we measure hydrogen and methane with our current breath testing, but we cannot measure hydrogen sulfide. Hydrogen sulfide is produced by sulfate-reducing bacteria in the gut and has been associated with numerous gastrointestinal disorders. Hydrogen sulfide is commonly associated with flatulence and diarrhea and can also alter gut motility and inflammation. So why do we need hydrogen sulfide breath testing? So as Charlotte discussed, we currently detect hydrogen, methane and also carbon dioxide as our proof that a patient has given a valid breath sample. Sometimes the patient does not produce any hydrogen or methane, but we might be missing the hydrogen sulfide. So we did a survey of 400 of our hydrogen and methane breath test patients and found that 17% reported flatulence and diarrhoea. 30% of these did have a normal breath test, but 6% had that flat line, so no hydrogen and no methane, apart from that carbon dioxide. If we were able to introduce hydrogen sulfide breath testing into our portfolio of tests, this would reduce the number of false negative results. It is also important, though, to understand that just because there's no hydrogen in a breath test doesn't mean that it isn't being produced. Both methanogens and sulfate-producing bacteria rely on hydrogen to produce methane and hydrogen sulfide, so the hydrogen could have just been consumed by these species. So in the past, we have tried to measure hydrogen sulfide. We initially tried with our current breath testing tubes filled with a mixed gas of hydrogen, methane, carbon dioxide and hydrogen sulfide and sent them off for analysis. This found all the gases except the hydrogen sulfide. We did give this a few attempts with numerous variations but with no success, so this was placed on our back burner until about a year ago when we discovered SIFT-MS. And also these PVDF bags. These PVDF bags are easy for patients to use. However, before we jump straight in with hydrogen sulfide testing, we need to assess the feasibility and stability of hydrogen sulfide in these bags. Stone kindly conducted stability testing of breath samples in these bags, as the main problem with sulfur compounds and breath bags is the adherence to the breath surface, particularly when stored for a long period of time. To test stability, the Stone team did a study where bags were filled 3 from a cylinder, 3 with breath, and 3 with a 50-50 split of breath and hydrogen sulfide. All the bags were filled at the start and analysed over the course of a week, with bag 1 being analysed on day 1 and 2, bag 2 being analysed on day 3 and 4, and bag 3 being analysed on day 7 and 8, just after a weekend. As you can see, the hydrogen sulfide concentration doesn't drop off over the course of these samples, but there is differences between the bags analysed on different days. So you can see that on day 1 and day 2 they're similar, day 3 and day 4 they're similar, and day 7 and day 8 they're similar. This just demonstrates the interbag variability and why replicates are really important when using these bags. However, you will also notice that 10 ppm is not reading as 10 ppm. It's more reading like 8.5. Now, when the cylinder was analysed on the SIFT, it read as 10 ppm, so the tank concentration is correct. The SIFT is measuring it correctly, so it's clearly an issue with the bag and the adherence to the bag surfaces. So we did have a think, what can we do to improve stability and get this 8.5 back up to 10? So Stone performed another study to assess if flushing the bags prior to use can remove the background from the bags and help prevent the hydrogen sulfide binding to their surface. So this time they filled the bags from the cylinder after 3 different pre-flushings. So 3 were pre-flushed with nitrogen, 3 were not flushed, and 3 were filled with just nitrogen to act as controls. These bags were all filled on day 1 and analysed over 5 days from the same bag. So we found that 10 ppm still reads as 8.5, so there's still clearly adherence to the bag surface despite clearing the bags out first. But this time the hydrogen sulfide concentration dropped as the days went on. This is a different design to the previous stability study where the bags were analysed on different days. Here, the same bag is being used over the 5 days and the bag's being open and closed. So this needed repeating to see if that still happened. So in the repeat, it had the same design as the stability, so all bags filled on day 1 and samples taken for 8 days from a different bag each day. This showed that flushing the bags reduced the variability between the bags and improved the stability compared to unflushed. So flushing definitely helps, but obviously doesn't get us back to that 10 ppm. So what do we recommend for hydrogen sulfide testing with SIFT and PVDF bags? So we say it would obviously be best for the patients to breathe directly into the SIF machine. However, obviously we understand that this is not practical, and not all settings have nitrogen for bag flushing. So the flushing has been repeated with the breath biopsy equipment, and it has been shown to work just as well as nitrogen. However, obviously it doesn't get us back up to that 10 ppm. We're also investigating if a patient using a breath filter when they breathe in before giving a sample will enhance the sample. So our recommendations are flush the bags with clean air before use, patients breathe out slightly before exhaling, give replicates of samples, get room air samples so it can be confirmed that the hydrogen sulfide is on breath, not in the room air. And this breath testing method could also be used to detect other compounds if other compounds are found to be beneficial, such as short-chain fatty acids, and some of this is being presented as a poster. So we wanted to do some hydrogen sulfide testing in a population to understand what a normal level would be. So we took 27 healthy participants and they did a 3-hour lateralized breath test with us with hydrogen and methane samples and also the hydrogen sulfide samples. And this was in accordance with the AGIP guidelines. So they didn't take any antibiotics for 4 weeks beforehand. They didn't take any pro-motility or laxatives for a week, and they also followed a low fermentable diet the day before and an overnight fast. Now, the hydrogen and methane breath samples they did every 15 minutes, and the hydrogen sulfide they did before drinking the lactulose, and then 45 minutes, 90 minutes, and 180 minutes after drinking the lactulose. And these are the results. So on the left is the hydrogen. So hydrogen responds to the diet the day before, so you get a nice low reading to start with, and then it starts to rise as the lactulose passes through the gut and the bacteria ferment it, peaking in the colon before declining. This is normal, this is what we expect. And methane, you're either a methane producer or you're not a methane producer. So that is why the error bars are quite large here. Again, it's pretty stable. Methane doesn't respond to the diet or the lactulose, it stays pretty stable. And this is the results for the hydrogen sulfide gas. So on the previous slide, the hydrogen and methane, that was measured in parts per million, but here this hydrogen sulfide is measured in parts per billion, so it is on a different scale. But within our cohort of healthy volunteers, you can see that this kind of sticks around that 20 ppb mark. There is a slight dip in the middle, but it does recover at the end. But yeah, you can see it's nice and stable and looks like all the healthy volunteers fit within a similar region. Now, there is another group that have done similar work. However, they did the hydrogen and methane measurements via the Quintron device and hydrogen sulfide via gas chromatography. And they also did the lactulose breath test, but in patients with symptoms, so symptoms like bloating, gas, abdominal pain, and they just had to follow a 12-hour fast prior. Now, as you can see, the hydrogen and methane are very similar to what we found, but the hydrogen sulfide, obviously they did a lot more samples, but theirs start around 30 ppb, so higher, but in the same region, but they get a sharp drop after 90 minutes, and then it doesn't rise again, it stays nice and low around 10 ppb. Now, these differences, are these because the patients had symptoms, or are these because we have some binding to the bags? Obviously, we don't know if they encountered any problems with the hydrogen sulfide. There are some theories as to why there is a drop, but there isn't time to go into that in this presentation. So the conclusions. So hydrogen sulfide can be measured with these PVDF bags and the SIF machine. However, there is some hydrogen sulfide that binds to the bags, so that is just a limitation. Flushing the bags does improve the stability and reduce the variability between bags. Samples are stable for 8 days, but replicates are important to try and minimise that variability between bags. We have found almost like a Expected healthy range of approximately 20 ppb. However, we do need to look further into non-healthy subjects, like those with those disorders, as mentioned early on, that are linked to high hydrogen sulfide. So just some acknowledgements. We really need to thank Alstone for their help with test development, sample analysis of this. We couldn't have done it without them. Functional Gut for obviously the help with the recruitment of the healthy volunteers, breath sample collection, and the volunteers themselves. They spent hours with us giving samples and also followed the strict diet the day before. So we really appreciate all the healthy volunteers. And that's everything. Any questions, just let us know. Thank you.
Brilliant. Thank you so much, Sarah and Charlotte. If you're able to unmute and show your cameras, we have a few minutes, about 5 minutes for questions. Can you hear me okay?
Yes.
Yeah.
Fantastic, fantastic. Yes, so a few questions have come through. The first is, there's already some commercial devices on the market which can detect hydrogen and methane. What do you see as the advantage of analyzing samples using GC mass spec?
So firstly, thank you for the question. A lot of these devices that are currently available to measure for hydrogen and methane often require patients to go into clinic to perform the test, either blowing directly into a machine or blowing into a foil bag, which hasn't got a lot of stability and the sample isn't valid for a long time, so it needs quick or immediate analysis. The machine that we use, the gas chromatography, we can use small little gas collection tubes, so patients blow directly into them, and when they do that, they've got a validity time of 2 weeks. So it means we can send the kit out to a patient at their home, they can complete the test in their home address, and as long as they ship it back to our lab within 2 weeks, there's no issue with analysis. So it means that patients can do the test completely themselves at home, which, as the tests are quite long, a SIBO test will typically take about 2 hours, and a carbohydrate malabsorption test can take up to 4 hours. So this is time that patients can spend at home. They can do it while they're working from home or working in an office, that kind of thing. It doesn't disrupt their day. They don't need to come in for an appointment, as with sort of more traditional breath testing devices.
Brilliant, thank you. And presumably in kind of post-COVID environment as well, it's helpful not having patients having to come into the clinic.
Absolutely, yeah. As the nature of breath test, it's considered to be an aerosol generating procedure, which requires a higher level of PPE. For a patient doing a test for 2 hours, they need to be in a room by themselves for 2 hours, which particularly in the NHS, there isn't the capacity to do that. So it just gives more flexibility, both for the patient and for the staff that are carrying out the test as well.
Brilliant, thank you. Next question is, could transit time be monitored by a combination with non-digestible carbohydrates that produce short-chain fatty acid after the small intestine, or a similar approach?
So transit time is something that has been attempted to look at before with a non-digestible sugar such as lactulose, but the issue with this is the variation in the microbiome and how that can affect the test. So for example, if you've got a patient with SIBO, they'll be producing these byproducts, short chain fatty acids, gases such as hydrogen, things like that earlier on. So it can give sort of a falsely quick result for transit time. And then inversely, if you've got species that are producing hydrogen sulfide or methanogens that aren't producing the kind of byproducts that you'd expect that are typically produced within the colon, it can produce a falsely slow result. So it's not the most useful method of measuring for transit time unless you do some sort of imaging with it, but there are studies that have tried to do it, particularly with lactulose, but it's the presence of SIBO, the presence of different microbiome can affect the results, unfortunately.
Brilliant, thank you. There's one here for Sarah. Did all the healthy volunteers produce similar amounts of hydrogen sulfide, or was there variation?
So most were within 10 to 20 ppb, but we did have some go down as low as 5-6 ppb, and some reach 50 to 80 ppb. We have seen some patients since that have reached over 100. So I guess it just obviously, whilst the vast majority were, there was probably one or two that would have been classed as positive for hydrogen sulfide.
Brilliant, thank you. Next question is, how do you see this test being offered with the current HMBT breath test? So I assume that's a hydrogen sulfide.
Yeah, So at the moment, we're doing it on a basis of if it's requested, or if a patient produces a flat line, we may invite them back in to do an extended hydrogen methane breath test with additional hydrogen sulfide samples. But in the future, we hope that we can offer this at home once we've been able to sort out using a breath filter in a home environment and work out backgrounds at home levels as well. But at the moment, it's just not quite ready for that.
Brilliant, thanks. And then we have time for one quick one. RH2 and CH4 breath test studies in the UK performed based on both the European and US consensus guidelines.
So European and US consensus guidelines in terms of preparation and the performance of the test are fairly similar. So the test that we do sort of adheres to both of them. And then in terms of the analysis, when we're analysing a breath test, we'll make a comment on whether it's positive by European guidelines, and then a comment if it's positive by the American guidelines as well. And then we consider it to be sort of a true positive if it's positive by both. And if it's positive by just one, then we look at other factors such as symptoms during the test, and generally let the consultant or physician who's requested the test come to their own judgment on whether they consider it to be true or placebo or not.
Brilliant, thank you so much. There's a couple of other questions, but we'll have to get those back to those who asked by the chat function. So thank you again for a wonderful talk and taking the time to present and answer the questions.